in preparation for the multimeter lab, I'm going to have to lecture on chapter 27 and talk about the multimeter lab. In that lab, you're going to show me that you've learned how to use the multimeter. Okay, so that was also a 2-week lab. So I'm going to talk about that next week. So at some point, I'm going to send you an email, say, please read chapter 27. It's probably the easiest chapter we'll go through this semester, and I figure good time to cover that in the lab. It's a quick chapter. Okay, so one thing I'd forgotten to mention to the other group, I'm almost all the way through grading your worksheet. I'm going to try to grade the worksheet today, and then grade the exam. If I don't get to the worksheet today, then I think what I'll do is just focus on grading the exam, because I think that's more important. So we're going to be starting on the new unit on electrostatics, and I need to say some things about charge. So I sent you folks a set of notes on properties of charge yesterday, and what I did was I took the first 6 or 7 slides from the chapter 23 notes and put them in here just so I can talk about them. So you might not see, as I go through the properties of charge lab slides, you will see a couple extra slides added in, but that's with your other set of notes. Okay, I just did it temporarily just so I can cover the material, so I can start on Coulomb's law right away and lecture. Okay, so our lab is going to be, you're going to be making a video on some phenomenon that you will observe, and you're going to explain them. So you're going to observe some phenomena and you will explain them. That's the lab. And so this video lab will probably be the longest one you'll be doing this semester. And I offer this mode of doing the lab I think it allows some students to be creative in writing or in working on this report, as opposed to just the drudgery of writing a long lab report where we have to explain a lot of things. So anyway, there's something different. Okay, so in order for us to know something about the property charge, or go ahead and do this lab, I need to say some things about charge. Okay, so my first 30, 40 minutes, I'm going to talk about some basics of charge. So I have a little outline of the history of electric attraction. And so before I talk about that, I want to say a couple things about concepts you've learned so far. Some of the basic measurements that you've learned in your physics courses. So in your first physics course, you really learned 3 basic physical measurements. One is called length. One is called time. Another one is called mass. And I write the word and I denote the fundamental measurements with a letter with brackets around it. And of course, for each one of these fundamental measurements, there's a set of units associated with them. And we can use these instead of units to do dimensional analysis. You've learned these in Physics 205, for example, or your first calculus-based physics course. Now, there's other fundamental measurements, and what I mean by fundamental measurements is that these can't be derived from anything else. Velocity, for example, comes from a length over time. Okay, so these are fundamental. So I'm going to introduce you to a new one called charge. And we can use a capital Q or small letter q to denote charge. The unit that typically associated with it is the SI unit of the Coulomb. Okay, so this is the fundamental measurement. This is the unit associated with the fundamental measurement. This is the SI unit of charge. There's other units, but we're not going to get into them. They're not talked about very often nowadays. This is the main unit of charge that we use nowadays. Okay, it's not like energy where there's so many different units of energy. So I want to spend a little bit of time talking about charge so that we can talk about the experiment, and furthermore, we can talk about Coulomb's law in lecture. So I list there some of the history involving experiments and our understanding of electrical attraction. And surprisingly, a lot of people don't know that Benjamin Franklin was a scientist. Franklin was not only a politician, but Franklin was also a scientist. And Franklin was responsible for introducing the idea of positive and negative charge. Both Franklin and Dipole in the 18th century observed that there's two different kinds of electricity. And what does that mean? Well, if you take a PVC rod and rub it with fur, and you take another PVC and rub it with fur, and you bring the two PVC rods together, you will find that they repel each other. If you take a PVC rod, rub it with fur, and then you also take a glass rod and rub it with silk, and you bring the glass rod close to the PVC rod, you will notice that they attract. Because those two materials were electrified differently, that's the term they used in those days, then they came up with the idea that, okay, well, if you charge them differently, there must be something different about how they were charged. And that's where the idea of like charges repel, unlike charges attract came from. Franklin also introduced the concept of conservation of charge. Around 1897, Thomson measured the charge-to-mass ratio of the electron. I will say something about it later on the semester. And then Millikan showed that charge is quantized and measured the charge of the electron. The charge of the electron is the basic unit of charge. The charge of the electron, I'll write it as Q sub E, is 1.602 times 10 to the minus 19 coulombs. We know this in more decimal places. Usually I'm going to write this as 1.6 times 10 to the minus 19. Okay. That's the basic unit of charge. And then for the proton, by the way, for electron, this is negative. For the proton, which is positively charged, this value is plus 1.602 times 10 to the minus 19 coulombs. All charges, any charged object, its value is derived from some combination of these two, a linear combination. So basically, if it has 2 electrons and 3 protons, they're going to take 2 times this plus 3 times that to get the total charge. That makes sense? So here's a list of basic properties of charge. They exert forces on each other, and they can be attractive or repulsive, as opposed to when we talked about the force between two objects that have mass. The gravitational force of attraction, it's always attractive. Right. Remember that the gravitational force of attraction is due to the mass. It has nothing to do with positive and negative charges. It has nothing to do with magnetism. It just has to do with the fact that objects have mass. Charge, just like mass, is a scalar quantity. It's just defined by how much, no direction. The only difference is that mass can only be positive. Charge can be positive or negative. Charge is conserved, and these are the basic units of charge. The magnitude is 1.602 times 10 to the minus 19. So I can do the magnitude of the basic unit of charge. Of course, the other elementary particle that we can talk about is the neutron. It's neutral. And in this course, we're going to assume that these are 3 elementary particles and that all charges are derived from multiples of these values. And I can use the term linear combination of these values. And it's true there are particles called quarks, which we've learned in the which we learned about in the 20th century, that quarks come in multiples of 1/3 or 2/3 of this value, but because we're not going to go inside the proton and inside the electron and inside the neutron, we're not going to deal with that. Let's ignore that for now. Quarks have never been isolated anyway. Okay. So, charges add. So if you have 2 electrons and 2 protons, the total charge, if you combine them together, is 0. The net charge of 2 electrons and 2 protons is 0. Whereas if you have 2 protons, their mass, a proton and an electron, their total mass is the sum of their masses. In fact, let me write down the mass of the proton and the mass of the electron. Because you don't put these on a scale, you determine them indirectly. So this is the mass of the electron. Notice how small that is, 10 to the minus 31 kilograms. The mass of the proton is of the order 10 to the minus 27 kilograms. The neutron is about the same value. It changes at the next decimal place, if I remember correctly. So I treat them as almost the same mass. And if you notice, if you write their mass in terms of the rest mass, in terms of MeV over c squared, you'll notice the difference, that the neutron's a little bit heavier. Okay, but you see that at the next decimal place. Again, one property of charge is that it's conserved. In one famous experiment, you can take an electron and slam it into its, an electron, there, slam it into its antiparticle called a positron. An antiparticle is a particle of the same mass but opposite charge. And what you can get out of it is 2 photons, which I'm denoting by this symbol gamma. Basically, two quanta that have just energy. So the mass disappears, it gets converted to energy, and you have 2 photons that go off in opposite direction. If you notice that the amount of charge I have on the left is 0, because the electron has minus 1.602 times 10 to the minus 19 coulomb. The positron has the opposite charge, plus 1.602 times 10 to the minus 19 coulombs. The sum of these two is 0. And what I end up with is the mass getting converted to energy. We know that's possible from relativity. And you have no charge on this side. No charge on the left, no charge on the right of this equation, showing that charge is conserved. In fact, the opposite of this is also possible, where you can have 2 photons of high energy slam into each other to produce an electron-positron pair. So this is called, when the arrow goes to the left here, this is called pair production. When the arrow goes to the right, this is called pair annihilation. Both have been observed. And they demonstrate the fact that charge is conserved.
What was it called when it goes to a proton to electron again? Or a neutron to electron?
When they annihilate? When
the other one.
Oh, the other one is called, the other one's pair production. So the photons interact with each other to produce two particles that have a finite mass. So this is called pair production. I guess I'll
Okay.
write it down. And you can calculate what's the minimum energy for this to occur because we've done this we talked about this in relativity. So that one's, with the arrow going to the left, is called pair production. And with the arrow going to the right, it's called pair annihilation. So in order for us to learn a little bit or understand a little bit about the electrical properties of matter, I got to say a few things about atomic structure. So I'm going to spend a few minutes talking about it. And you might have seen some of this stuff in chemistry already if you've had chemistry. But anyway, I want to go through it. So the basic constituents of matter, okay, ignoring quarks and things like that, are electrons, protons, and neutrons. And so they form atoms, they form ions, and they form molecules. So let me say a little bit about them so you have some general knowledge. So let's look at a neutral atom. They have the same number of protons and neutrons. I'm sorry, same number of protons and electrons. And we'll use the letter Z to denote the number of protons and electrons. So this is neutral. Okay, uncharged. So for example, a hydrogen atom. You have a proton here. And then the simple-minded model has the electron going around the proton. This is not correct because the electron is actually a wave. So is the proton actually. We treat them as waves. But the first model of the atom assumed that the electron was going around the proton in a circular path. And that's something that's covered in 215. But then after the model, the correct one is that these are treated as waves. Okay. And you can have this version of the atom, the same atom, with an extra neutron in it. So you can put a neutron in it. It's the same atom because it has the same number of protons. This is called deuterium. This is, of course, this is hydrogen. The nucleus is called a deuteron, which I discussed at the end of the unit of relativity. They're the same atom, but they're two different isotopes of the same atom. So when I change the number of neutrons in the atom, I have different number of isotopes in the atom. For example, uranium, which has 92 protons and 92 electrons, comes in many different isotopes. So there's different versions of uranium with different number of neutrons in the nucleus. Just to give you an idea of the size of these things, the nucleus, the atomic nucleus, is of the order of 10 to the minus 15 meters. The diameter is of that order. Okay, that's what this means, order. The atom itself, the size of the atom, which is really defined by where the outer electron is about 10 to the minus 10 meters. So there's a lot of space between the electron and the proton in an atom. Even if it's a big atom, there's a lot of space. I mean, this is a factor of 100,000. Just scale it up to our size, what that means. Just imagine a distance that's 100,000 times your height. If you're 6 feet tall, and just imagine something 600,000 feet away from you. That's what it'd be like if you scale it up. Because there's a lot of empty space here. Okay. Now, we can have atoms with an electron removed. We can have atoms with an electron added. Those are called ions. Of course, we can say the same thing with molecules too. So what about ions? Well, an ion is an atom with an extra electron or extra proton. So if I take off the electron from this hydrogen atom, I have an excess of positive charge equal to whatever the charge of the proton is or charge of the electron is. And so I write it like this. By the way, if I wanted to write the symbol, if I want to differentiate between hydrogen and deuterium, here you have one proton, one neutron. Here you have one proton, which is about what's called one atomic mass unit. The bottom number represents the number of proton you have in the atom. Okay, so this is a hydrogen atom. Obviously, since it only has one electron, that's the most you can take off. How many electrons can you take off in an atom? Well, you can actually go into a lab, for example, and produce a beam of uranium atoms. This has been done in labs. You can take the uranium atom. The uranium atom has 92 electrons. And 92 protons, and you can strip off 91 of them. That's been done in the lab. I mean, these are isolated, right? These are isolated atoms, so you can strip off 91 of them. Of course, they're very highly reactive. They want to pick up electrons really bad when you take out 91 off them. But you can create a beam of them in the lab. Okay, so that's a highly charged ion. Okay. You can also have atoms with an extra electron on it. And it turns out the most electrons you can add to an atom is 1. No one has ever discovered an atom with more than 1 electron added to it. And I'm talking about an isolated atom. And in fact, there's some atoms you can't even add an electron. So the most famous one is nitrogen. You cannot, in a lab, add an electron to this thing so that it stays attached to the nitrogen atom. Zinc is another one. You can't add an electron so that it sticks to it. And again, I want to reemphasize this. We're talking about isolated atoms. Okay, I mean, in other words, forming a beam of them. Okay, so the most electrons you can add is 1. The most electrons you can take off, well, it just depends on the size of the atom. Okay. Now, there's things called molecules. Molecules are combinations of atoms. Most famous molecule was probably H2O. All right, that's a molecule. There's all different kind of molecules you can think of. If you had chemistry, you can have, if you had OChem, you can probably think of all kind of complicated molecules that I had never heard of. Okay. And they all have electrical properties. And the electrical properties that they have are based on what the electrons do. Okay. The electrical properties really depends on the behavior of the electrons in the material. So you can have a hydrogen molecule, you can ionize it, for example, and now you have an ion. Now there's a special type of molecule where you can group a bunch of them together, and these are called clusters. And I don't know if you talk about them in chemistry class. This has been around since maybe the 1990s, or maybe late 1980s. People have been talking about clusters and their properties. The most famous one is C60. This is the shape of this is in a soccer ball. It's known as again, it's a buckyball, and when this was discovered, this formed the beginning of our nanotechnology. This is something, because it's bigger, you can actually add 2 electrons to it. The problem with adding electrons to the atom is the electrons want to repel each other. Because the electrons are far out in the nucleus, and because they're moving around all the time, their average positions in the atom produces a net repulsion between them, and so it's very hard to keep the extra electrons. But when you have something big like this guy, you can add an extra electron. And there's some molecules out there that are predicted to be able to hold 2 electrons. Okay, and a lot of them have been produced in the lab. And again, so I'm giving you a little bit of an idea of atomic structure, but again, the electrical properties depend on what the electrons do. And how these combine to form a solid or liquid also affect the electrical properties of the material, because when you combine atoms together to form a solid, or when you combine molecules to form a solid, the molecules themselves, or the atoms themselves, will also interact with each other, which I'm not going to get into here. So let me talk about the 2 different kinds of electrical materials, and I'm going to simplify things a lot here. I'm going to only talk about 2 types of electrical materials: those that conduct electricity and those that don't conduct electricity. Those that conduct electricity, we're going to call them conductors. These are materials in which the electron can flow very easily in the medium, like aluminum foil, like copper wire. The electrons can flow very easily through them. Why? Well, the reason why is because when you bring together, for example, a bunch of copper atoms to form a wire, the force between the atoms causes the electron, the outer electron in each of the copper atoms, to be very loosely bound to any atom. And they can flow freely within the material, almost like a fluid. Just to give you an idea of this, I'm going to do a demonstration illustrating this. So I have a can. All right, I have a can here, and now I'm going to show you how easy it is to make the electrons move. This can is uncharged, so I need to do something. I need to magnify my display. I have a table, a little table so I can do demos. Let me magnify a little bit more, and you can all see the table. I don't want to magnify too much, or otherwise it'll get blurry. So I'm going to take this. It's neutral, okay? I have a PVC rod. I'm going to charge it, and I'll talk about how this thing gets charged in a little bit. I'm going to rub it with fur. I don't know if you can hear the static from me rubbing. Oops. Well, let me do it one more time. My can has a label on it that I should have taken off. You can see, I hope you saw, that the can was attracted to my charged rod. So what happens? This rod, I mean, if you do an experiment, you'll find that when you charge this rod, let me change the view again. When you charge the rod, it becomes negatively charged. When you charge this, it becomes negatively charged. When you bring it near the can, which is a conductor, it's a metal, the electrons are free to move. The electrons in the can do not like the electrons, the negative charge on the rod. So the electrons in the can run away essentially to the other side of the can, leaving a net positive charge on the side near the rod. Since you have a negative charge on the rod and a positive charge in the vicinity of the rod from the can, they're going to attract each other. In fact, if my rod was positively charged, and I didn't bring a positively charged rod, but if this rod was positively charged and I brought it near to the can would see the positive charge. The electrons in the can like the positive charge, and they would rearrange themselves to get as close to the positively charged rod as possible. So now you're going to have a net negative charge on the surface of the can. There's the rod, and that's going to cause the can to be attracted to the rod. So no matter what, the can will be attracted to the rod even if the can is uncharged. Does that make sense?
Yes.
Okay. And that's always going to be the case. And that's because the electrons are free to move and the effect is strong. And you will see it in the lab because you're going to do essentially the same thing. So I'm going to have, even though I showed you, I'm going to have you demonstrate it so you can see it work. So you can see it work yourself. Okay. Now the opposite of conductors, the total opposite of conductors, are insulators. I should say that we're ignoring the idea of semiconductors here. Let's not worry about that for now. Insulators are materials where the electrons can't flow very easily. Insulators have a special property, though, called polarizability, which means that you can actually separate the average position of the negative charge in the material from the average position of the positive charge in the material. In other words, you can form a dipole in the material. And these materials are called dielectrics. Some materials are already polarized. Some materials, the position of the negative charge in the material is separated from the position of the positive charge in materials. Can you think of any materials that are inherently polarized? Can you think of anything that's considered polar? If you've had chemistry. Yeah, but we're talking about electrically separated. What about water? The water molecule. The water molecule is a molecule that's inherently polar. The negative charge is separated from the positive charge. That's a polar molecule. And so you can actually see electrical effects fairly easily with water. But you can have materials where you can separate the average position of the negative and positive charges. Let me just draw a quick picture. Suppose I have an insulator. And I take a rod that's negatively charged. Bring it next to the insulator. And let's focus on one of the atoms or one of the molecules that make up this material, whatever it is, wood, a wooden block, whatever. If I do this, then the molecules in here are not going to like these, the electric charge in the molecules are not going to like this negatively charged rod. And so the negative charge will be pushed away, leaving the positive charge at the front. And what you'll form is called something called a dipole. You're going to induce a dipole. You're going to separate the positive and negative charge, and you're going to form a dipole. Whoops, 1 second. Okay. And the dipole basically, again, is just a separation of two equal but opposite charges. And we give it a definition. We define it as the letter P equals Q times L. L is a vector that points from the negative charge to the positive charge. So this is L. The size of the charge is basically Q. This is the magnitude of either of those two charges. L is the vector that points from the negative charge to the positive charge. So this is called a dipole moment. And really, I should be more specific. I should say it's the electric dipole moment, because there's also such thing as a magnetic dipole moment, which we're probably not going to spend a lot of time discussing. Okay. So what do you think is going to happen when I bring this rod next to this insulator? I have an excess of positive charge here. Imagine I do this with a bunch of materials. I look at a bunch of the molecules here in this material. What's going to happen? Well, you're going to get a whole bunch of positive charges. Like that. Let me show you a picture. Actually, the picture I'm showing you right now shows you material that's polar. This is a material that's not polar, but I polarized it by, or at least I polarized it temporarily by bringing this rod near it. The picture I'm showing you in the PowerPoint, you have a material that's already polar, but the dipoles are randomly oriented. And when I bring the charged rod near it, the dipoles get aligned. Now, this picture that I'm showing you is exaggerated. The alignment of the dipoles is completely exaggerated. Not every single dipole in the material will get aligned. Okay, maybe locally they will be. The ones closest to the rod will get aligned. But the idea is you're going to get a general alignment of the dipoles in the material towards that charged rod. In this particular case, you will get a general alignment of the dipoles towards the rod. Out here, you probably won't have any dipoles. Everything that's going to occur is has to do with whatever's near the rod.
So really, the top dipole and the bottom dipole would be angled toward that rod?
Correct.
Okay.
You're correct about that. Okay. And same thing in the figure. And I stole that figure in the PowerPoint off the internet. That's generally how they draw it, but that's an exaggeration. Okay. Okay, so I guess what I should do is try to do a demonstration of this effect. So again, I'm going to go back and change my view here. I'm going to magnify a little bit. Now granted, I'm going to say that what I'm going to do here works best with the equipment from campus. Actually, let me do this. I don't know why I have that there. So I have, usually if I'm on campus, I can get a Petri dish to do this, but I wasn't able to get a Petri dish. So I have basically this is a strainer that I put upside down. And this is it's not a 2x4, but it's a board. 1x4. Let me balance it. Okay. And I want to see this effect. I want to try to see this effect. I want to polarize the charge in this 2x4 by bringing the charged PVC rod next to it and see what happens. Do I get any noticeable effect? Do you guys see the board moving? It's a weak effect because the material in here is not polar. I have to polarize the charge. You see the board moving? Okay. So
Yeah.
I can actually get that board to move. It's a weak effect. Why? Because I have to polarize the charge first before I see the attraction. If this were a metal bar, although the metal bar would probably be heavy, the effect would be more pronounced because the electrons are more easily free to move. If the material was polar, then the size of the effect would be somewhere in between the metal and the non-polar material. So the strength of the effect is going to really depend on whether you have a conductor, whether you have a polar material, or whether you have something that's non-polar. You have to induce a dipole in the material. Okay. Somebody asked a question this morning, how big is the effect if you let's say put water on it? And I said, yeah, it'll probably change because of the fact that the electrical properties are different. By the way, the only way I can get this to work is if I balance this at a point. Okay, that's why I'm using a bowl. If I had this on the table, it would never work. Too much friction. I wouldn't have enough of a force to overcome the friction. Okay. So I'm hoping you saw that okay. Let me go back and change my camera. Okay. By the way, I'm going to say a little bit more later on, not today, but about dipoles, because there's a lot of interesting physics that one can do with the concept of dipole. The idea of dipole can be used as a tool to do approximations to difficult problems. Those of you who take 215, when you talk about the mass on the spring problem, that problem is also very important because that system can also be used to approximate difficult to analyze systems. This one does too. So I'll say a little bit more about this. I won't have time for it next week, but maybe in a couple of weeks, I will have a discussion of dipoles. Okay? I want to talk about how things get charged. When I take a PVC rod and I'm rubbing it with fur, I am transferring charge from the fur to the PVC rod. In fact, the PVC rod becomes negatively charged The fur becomes positively charged because it's losing its electrons. It's only the electrons that move. The positive charge doesn't move, because if the positive charge move, you're changing the atom or the molecule completely. So what governs this? Is it friction that governs this? And you can go on the internet and you'll see a lot of sites say, this is called charging by friction. Right? You'll see a lot of internet sites will say this is charging by friction, and I don't think that's accurate. I wouldn't say I don't think it's accurate. It's not accurate. The reason why charge gets transferred from one material to the next is because of the fact that one material likes to pick up the electrons, the other material likes to give them away. So people have done experiments and they've developed a table listing what materials like to pick up the electrons and what materials like to give them off. They call it a triboelectric series because this is called, charging by contact is called triboelectricity. And what they list here, they assign a number, a value that describes how well they'll pick up a negative charge, or how well a material will give off negative charge. Okay. So if you have two materials, you're rubbing two materials together that had the same value in the triboelectric series, do you think you're going to be transferring charge? Answer is no. It ain't going to happen. You can be rubbing as much as you want, producing as much friction as you want. If the two materials have the same electrical properties, you will not be transferring charge. Okay? So what really dictates charging by contact is the fact that one material likes to pick up charges, negative charge, the other one likes to give them off. Friction is the conduit that allows the charge to be transferred. But it's really not, to me, it's really not the reason why charge is being transferred, because if you have two materials that have the same electrical properties, nothing's going to happen. If you take two pieces of PVC rod and rub them together, you're not going to charge either one of them. So charging by friction, saying it's charging by friction is misleading. You just say charging by contact, that's it. Friction means that the materials can interact with each other to transfer charge. Right? Friction's always going to be there. When you rub two things together, friction's always going to be there. But what causes the charge transfer is the difference in terms of whether they have to be electrical opposites. One likes to give off the electrons, the other material likes to pick them up. Make sense? Now suppose I do the following. Let's say I have an isolated conductor.
We cannot see your computer screen if you're still sharing that.
Sorry. Thank you. You okay now then?
Yep.
Okay.
Thank you.
Yeah, so I can show two different screens at once on this thing, so I apologize. So let's say we have an isolated conductor. Okay? And of course, if you have an isolated conductor, I didn't do that very well. You have an even number of positive and negative charges. Now let's say I take a positive charge or a negative charge and bring it near the conductor, what's going to happen? Well, if this in this conductor, it's still isolated. I mean, there's no electrical connection right now. What's going to happen is the electrons are going to want to run away. And again, I'm exaggerating this effect in my picture. These probably would be more bunched. Actually, these probably would probably be more like this. But I think you get the picture. And then you'd have a lot of positive charge here. And what I've done is temporarily induce charge on both surfaces. Of course, if I remove this, then the charge will rearrange itself so you go back to this configuration. And it'll probably happen within 10 to the minus 16 seconds. That's the estimated time. Of course, we don't have a way to measure that. At least not now. What if I take a wire and I attach it to, let's say, a water pipe, which goes into the earth? This is called grounding. I guess I should answer the question, what is grounding? Well, what is ground? Well, you're sending a wire, or you're giving electrons a path into the earth. Earth ground can be considered as either a sink or a source of electrons. The earth is big, it has a lot of electrons in it, or it can take up a lot of electrons. Okay, it could be a sink of electrons, like the sink in your drain, or it can be a source of electrons, like your water faucet. So what happens when I connect this to something that goes to ground, earth ground? These electrons are going to see a path towards earth ground. So these electrons are going to go down this way, and they're going to be happy because they don't want to be close to this negative charge. Now, while this negative charge is still there, I disconnect the wire. Now what? What happens when I do that? I'm left with a positively charged conductor. This is charging by induction. This is what you're doing with the electrophorus. Okay? This is what you're doing with the electrophorus. Let's call it charging by induction. You're not charging by contact. I mean, I know, granted, you're touching a wire, but you're not rubbing two things together. Does that make sense? So this is another way to charge the material. Now, and this is what you're going to be doing with the electrophorus. So in this lab, you're going to be looking at charging by induction and charging by contact. You're going to be looking at both those methodologies. And by the way, when you look at the lab, I forgot to get rid of a couple of things in the lab. There's in some steps, it alludes to using a glass rod. I've gotten rid of the glass rod from the lab because students last semester had a hard time getting the glass rod to work. Glass rods get positively charged. If we were on campus, I would leave that in because I can walk into the lab and make it work. But it's a lot harder when you're doing this at home. So I got rid of the glass part of the lab. So I'm going to make a couple corrections to the lab to get rid of the part that mentions glass rod in it, okay? The glass rod and the silk. So you don't have to do that part. Okay, so there's actually another way you can charge by induction. I'm going to show you that real quick. You don't have to even touch anything to ground in doing this. So let's say I have a conducting metal sphere with an insulator. So that's an insulator. This is a conducting sphere. and I take, just for fun, we'll make this rod positively charged. Let's pretend it's a glass rod. I bring it near this conductor. What's going to happen? Well, the electrons want to be close to this rod, and then the positive charge is going to end up, you're going to be left with positive charge here. Okay, so that's the same thing as what I showed you with that isolated conductor. Now let's say I take another one of these spherical conductors and just put it in contact. And what's going to happen? The electrons from this conductor are going to go here, and you're going to be left with a positive net charge here. Okay, again, my drawings are exaggerated. I'm just showing a positive, a negative net charge here and a positive net charge here. I'm not saying that all the positive charge is gone here, and I'm not saying that all the negative charge is gone here. I'm just saying is that I'm going to have an excess of negative charge on the red sphere and an excess positive charge on the green sphere. Okay, so I have that. I'm going to keep this rod there. I pull these apart. Now I'm going to have the red sphere will be negatively charged. The green sphere will be positively charged, and I've charged them by induction. That's another way to charge by induction. We okay with that? So I've created a poll. I have a poll question for you folks. Let's give me a second. And I'll open up the poll. So do you see the poll on the question?
Yes.
Okay, so you have this scenario. You have 5 styrofoam balls. They're suspended from insulating threads. Several experiments are performed on the balls, and these were the observations. Ball A attracts ball B and repels C. Ball D attracts B and has no effect on E. A negatively charged rod attracts both A and E. And the question is, what is the charge on each ball? So go ahead and think about it for a minute or so, and then choose your response. And this is completely anonymous. It doesn't show who said what. So far I have one person who's responded, so I need 6 more responses, not 5 more responses. And I'll show the class what everybody has, what responses everyone has chosen. I just need one more person to respond and we're almost there. So one person, go ahead and make your go ahead and respond. Okay, thank you. All right, so I'm going to end the poll. I have everybody's response. I hope you're feeling okay with your responses. We'll see. Here's the results. You guys all see the results?
Yeah.
Okay, so I'm going to stop the sharing and then talk about this problem. So I got a nice distribution of responses. I had a bigger distribution in the other group. Okay. So, okay, let me get up and talk about this one. So it says that ball A attracts B and repels C. So that means that A and C have the same charge. So A and C, same charge. And B attracts A. So B has to have different charge. Those two demonstrations that I did, what did they show to you? What do those two demonstrations I do show to you? What do they teach you?
That different charges push away from each other.
Well, remember that in both cases, the object was uncharged, right?
Yep.
And whether it was metal or an insulator, the uncharged object always is attracted to the charged object. Correct?
Yeah.
Okay, so let's look at statement 2. It says ball D attracts B, but D has no effect on E. So what does that say about D and E?
Both neutral.
Yeah, D and E have to be neutral. Okay, that's what that statement tells you. Now, the last statement. A negatively charged rod attracts both A and E. Well, if the rod's negatively charged and it gets attracted to A, then that means that A and C has to have a positive charge. And then we know that D and E are neutral. So all we're left with is B. Well, B attracts A, so that means B has to be negatively charged. That's your answer. That's D. It's like one of those SAT exam questions. Okay. So the answer to that one was D in our case. Any questions on this? And if their balls were metal, you get the same answer. All right, so let me...
So even though E is neutral, it still got attracted to the negative?
Yeah, the negatively charged. That's what we did here, right? I mean, that's those two demos. I mean, my PVC rod, when I did the demo with the board, this thing was negatively charged.
Oh, okay.
Right.
Okay.
Okay.
That makes a lot more sense.
Okay, good. Yeah, and it's... These questions they get you to think. They're not easy questions. But they get you to think a little bit about the properties of charge. And I asked this question to help you with the lab. So let me discuss the lab here real quick. The procedure is simple, so there's nothing complicated about the lab itself. Let me scroll up a little bit. So you're going to create a video either on Canvas or on YouTube. And basically what you're going to do is observe and explain. And there's some things in here I forgot to remove, like the silk, because I don't think you have silk in your lab kit. And I got rid of the part where you have to use glass because it doesn't work well. So in part one, there are 3 phenomenon you're going to observe. And what I want you to do in the video, because the 3 phenomenon have essentially the same explanation, I want you to pick one of them, the one that works best for you, demonstrate it and explain it. Okay, so out of these 3, just pick one to explain. Really, what you should be doing is try all 3, see which one works best for you. Okay. Part 2, that's where you use the electroscope. And if you notice in step 1, it says charge the glass rod. Do not charge the glass rod. You don't, the glass rod doesn't work very well. Okay, because your electroscopes aren't very fancy. So basically what you're going to do is look at how the electroscope works, how it demonstrates that things are charged. Can you design an experiment that indicates whether something is negatively charged or positively charged? Okay, that's what this part is for. And the last part is electrophorus, which demonstrates charging by induction. And basically it has you 2 different experiments where you change the distance from the metal plate to the insulator that you charge. It's either styrofoam, because I used styrofoam the other day when I showed it to you, but you can also use saran wrap or you can use a transparency. They work okay also. And again, you want to observe and explain these items. And really that's it. I mean, they're pretty straightforward. To be honest, when it rains, the electrophorus doesn't work as well, because when you have more moisture in the air, the charge, it's harder to charge things up because water is a conductor. And the charge drains off faster from a material because water is a conductor. I have a rubric for the experiment listed there so you understand what I'm grading on. And I will say generally, the grades on the videos tend to be higher than on the written labs. Okay, I don't expect anything fancy when it comes to making the videos. In fact, you don't even have to make a single video. You can make multiple videos and send me the link to multiple videos. You can make multiple videos and then join them together into a single video. That's fine with me. Just do whatever works for you. As long as you can, I can see that you demonstrated the effect and you explained it. That's all that matters to me. Okay, that's really all I want to see. What I want you to avoid, though, is to, and I had this last semester, I had a student who gave me a 40-minute video of this experiment because the student did the experiment at the same time they're basically doing it for the first time. They should have, what you want to do is try everything out, see what works best, and then video it. Because it shouldn't take you that long. Do you folks have any questions or concerns? Was everything clear to you? Anything that needed further explanation?
So when you were saying for the part one, just pick one of those.
Just pick one of them, yeah. I mean, ideally, as an instructor, ideally, the instructor would like to see the student try all three and then use the one that works the best for them. Because,
All right.
because it's possible that one might work better for you than the other ones. And the reason why I just have you choose one, because they essentially work on the same principle. So if you can explain one, you should be able to explain the other ones.
Okay.
Yeah. Other questions? Oh yeah. Oh, before I forget, you try to use the terms I mentioned today, like polarization of charge, electric dipoles. Use those terms. I want to see that you integrated the stuff I said here into your experiment. That's something I'm looking for. Okay. Be careful if you look up explanations on Google. They're not always accurate, especially when you look at when they talk about charging by friction. That's not, to me, it's misleading. Okay. All right, so if you don't have any questions, then I'm gonna end it here. I'll see you too. Please bring your questions next week. And you guys are going to be filming this weekend, right? I guess, for the electrophorus, unless you've done it already. Okay. All right. That's it then. I'm going to end it here. I'll see you too.
All right. Thank you.
All right. You're welcome.